Next topic is Eulerian and Hamiltonian graphs. They are special kinds of graphs. So if you have a path in the given graph which contains all the edges of the graph exactly once, such a path you'll call it is an Eulerian path. And if it is a circuit itself, you have a circuit or cycle which contains all the edges exactly once. Such a circuit you'll call it a Eulerian circuit. And a graph containing Eulerian circuit is called Eulerian graph. Okay, so you consider the example G1, the graph G1, it has 4 vertices and 5 edges, right? So is it there, does there exist an Euler path? You consider the path starting from B, D, C, B, A, D. Okay, so this path starts at B and ends at D. It uses all the edges exactly once. We haven't traced any edge more than once. All the edges are used exactly once, and it contains all the edges and exactly once it is containing. Therefore this path you can call it say Euler path. It's not an Euler circuit because the starting and end vertices are different. Now, does there exist an Euler circuit here? If you consider the circuit, say A, B, C, D, A, it's a circuit, but it doesn't contain one of the edge, right? And if you consider any circuit here, it is not going to contain all the edges. You can see that only using all the edges exactly once you cannot find a circuit here in this graph. So there is a characterization that we are going to see which says Euler graphs will have all even degree vertices. So in this graph you have an odd degree vertex, 2 odd degree vertices are basically there. So this graph is not going to be Eulerian by that condition, that result. So that condition you can use, or that result you can use to check whether the Euler circuit exists or not, right? So if that condition is satisfied, then only the graph will be Eulerian, and if that is satisfied, then you can try to find such a Euler circuit. Now the graph G2 in the example, is it Eulerian? Does there exist an Euler path also? Both you can check. So suppose I start at the vertex A, go to B, then to E, then to C, then to D, then to E, then to A. So this is a circuit. So it's a path, it's a circuit also. It's starting and ending at A, therefore it's a circuit. Now this circuit or path used all the edges exactly once. So this particular path was Euler path, and this it's also a circuit. So this is an Eulerian circuit you are having. Since the graph contains an Euler circuit, you can call it an Eulerian graph. So this graph is Eulerian. Okay. Now yeah, so it's an Euler graph or Eulerian graph, you can say. Now the necessary and sufficient conditions for the existence of Euler cycle and Euler paths. We have 2 theorems. One theorem says if in the connected graph, so for Eulerian graph and Hamiltonian graph, for both we require connected graphs only. In connected graphs only it is defined. Okay. So for a connected graph, it will contain an Euler cycle if and only if all of its vertices are even degree. So this is one characterization. Another result is the connected graph contains Euler path if and only if there are exactly 2 vertices of odd degree. Okay, so that was the case for the previous example. We had a Euler path but not an Euler circuit, because odd degree vertices are there. There is no Euler circuit by that theorem, but there are exactly 2 vertices of odd degree. This vertex is 3 degree, this is 3 degree, this is 2 degree, this is degree 2. So there are exactly 2 vertices of odd degree, and the result says there will be an Euler path, and we were able to find such an Euler path, right? So this characterization or necessary sufficient conditions you can use for checking a given graph is Eulerian or not. If it satisfies the Eulerian condition, then you can go for finding the Euler path or Euler circuit, whichever is required. Okay. So now the next type of graph is Hamiltonian graph. In the Hamiltonian graph, or Hamiltonian graphs, basically the similar way you'll define it's a graph containing Hamiltonian circuit, and Hamiltonian circuit will be a Hamiltonian path which is a circuit. Now what is a Hamiltonian path? Hamiltonian path is a path in the graph which includes all the vertices exactly once. Other than the initial and final vertices, all the vertices are used exactly once. Such a path you'll call it's a Hamiltonian path. Now for a Hamiltonian path, if it's a cycle, it means the initial and final vertices are the only vertices which are same. Other than that, no vertex is repeated. In that case, we'll call it is forming a Hamiltonian, that graph has a Hamiltonian circuit or Hamiltonian cycle, right? So such a graph, if such a Hamiltonian cycle is there, we will call the graph is Hamiltonian, right? If Hamiltonian cycle is existing, the graph is Hamiltonian. Now consider the graph, the previous example graph itself. This one had an Euler path, but it is not Eulerian because there is no Euler circuit. But does it have a Hamiltonian path? You take the path A, B, C, D. Now there are only 4 vertices. This particular path contains all the vertices exactly once. Therefore, it's a Hamiltonian path. Now if you take the path A or the circuit A, B, C, D, A, this also contains all the vertices exactly once other than the initial and final vertex A. So this cycle, this path is now a cycle, and this cycle has other than the initial and final vertex, so all the vertices are used exactly once. So this is a Hamiltonian cycle. In this graph, Hamiltonian cycle is existing, therefore it's a Hamiltonian graph. This graph was not Eulerian, this is Hamiltonian. Okay, now you consider this graph. Here you cannot find a Hamiltonian cycle. There is a Hamiltonian path, but A, B, C, D, this path if you take, that's a Hamiltonian path, but there is no Hamiltonian cycle, right? So I can form a cycle this way, but it is not going to include the vertex A. Now any cycle you form which contains A, and which contains A, it is going to repeat one of the vertices, right, other than A, right? So you can go to A, B, C, D, B, A. This is a cycle, right? It starts and ends at A. It's a path which starts and ends at A, but B is going to be repeated in this case. Okay, so there is no cycle that you can find. Any cycle containing A will be visiting B 2 times, right? We have to go to A and come back from it, so we have to visit B 2 times. Therefore any cycle containing A will be repeating B 2 times. Okay, now if you so you can start a cycle from B in this form. It is going to C, D, then B, right? Now it's a cycle, but it's not containing A. Now if you go to A and come back, right, in that case we have B used 3 times. Initial and final vertices are B, but other than that B is used one more time. Therefore this cycle is also not a Hamiltonian cycle. So there is no Hamiltonian cycle here. It's a non-Hamiltonian graph, right? It's not an Eulerian graph also, because this edge, if you have to use it in a cycle, then you have to repeat it, right? So this edge is once used, you have to repeat it to form a cycle. Okay, so it's starting from the vertex A, or in any cycle this edge is used, right? So then that cycle to be formed, this edge has to be used more than once. So it's not going to be an Euler cycle. So other than that, you can also check the degree, the equivalent condition. You have a odd degree vertex here, right? There is actually 2 odd degree vertices in this graph. So if the odd degree vertices exist, it's not a Euler graph. So it contains an Euler path, but what is that? Is A, B, C, D, B. This is an Euler path. Okay, because of that result we know it exists, such an Euler path exists. There are exactly two vertices of 4 degree. Okay. Now you are given this graph, you are asked to check whether or show that it's Eulerian. So there exists such a, sorry, it's Hamiltonian, not Eulerian. This is a Hamiltonian graph, that's what you want to show. You can also check whether it's Eulerian, check the degrees of each vertex. Right, you are having this J, it is having degree 3. It's having degree 3. So there is an odd degree vertex, so there is no Euler circuit in this graph. The graph is not Eulerian. Now is it Hamiltonian? So check this particular path. You try different paths, you will be reaching a similar path, which similar cycle, which is which will contain all the vertices exactly once other than the initial and final vertex. Starting at A, if you want to find a Hamiltonian circuit, so we can go to say H. So visited H. Now to C, then to F, then to E, then to D, to G, then to B, then to I, then to K. We have to go now inside to cover here and come back to K, to J. So H is already taken, G and F are taken, so now to J, and then to A. Okay, so we started at A, we came back to A, we have used all the vertices of the graph exactly once other than A, which is only repeated at initial and final position. Therefore this cycle we got, it is a Hamiltonian cycle, therefore the graph is Hamiltonian. Okay, now a graph which is Hamiltonian but not Eulerian. Hamiltonian cycle is there but not Eulerian cycle is there. So you can consider any graph which has cycles but has vertices of 4 degrees. So this is one such graph. K4 if you take, you have, it is going to be Hamiltonian. You can take the outer cycle, right? This cycle you can take. This is going to be containing all the vertices exactly once other than the initial and final vertex. Now you have odd degree vertices, therefore the degree of vertex B is 3. So from that itself you can say it's not going to contain any Euler circuits. This graph is not Eulerian but it is Hamiltonian. It contains a Hamiltonian cycle which is A, B, C, D, A. This is the Hamiltonian cycle you can have. Okay. So without specifying the edges, I have written this. So if you are specifying the edges also, you will be writing it like this: A, E1, B, E2 to E2 with E2 go to C, then with E3 go to D, then with E4 go to A. So such a Hamiltonian cycle is existing. Therefore, it is Hamiltonian. And we have seen an Eulerian circuit before, Eulerian graph before. This graph is not going to be Hamiltonian. If you use any cycle in this graph which contains all the vertices, that cycle is going to repeat one of the vertex. If it is, so it is going to repeat one of the vertex more than once. So if you use this cycle which is starting at A, it is going to repeat E 2 times. Now any cycle at B, C, D, A which contains which contains all the vertices, that is going to repeat E. Okay, now we have to go to this section and come back, so that's why it is going to be repeated twice. Now if you start a cycle at E itself, what happens? E to A to B to E, then to C, then to D, then to E again. E is going to be repeated 3 times. So other than at the initial and final position, you are having E is repeated, so that it is not, that cycle is again not a Hamiltonian cycle. So there is no Hamiltonian cycle here. This graph is an example of an Euler graph which is not Hamiltonian. So you can have graphs in which cycles are there which is neither Hamiltonian and nor Eulerian. So such graphs also you can give. So you consider this graph. Okay, this graph, you know, it is not Eulerian, but it is Hamiltonian. Okay, now if you add a part here which is similar to this one, okay, add a triangular part there, so this one. Now for this graph, it is neither Hamiltonian nor Eulerian. This is not Eulerian because you have an odd degree vertex. That's enough to say it's not Eulerian. Now if you choose any cycle which contains all the vertices, if you start from this section, you consider this vertex as the reference. Now start from left side, any vertex you start a cycle, it is going to, if it is containing all the vertices of the graph, it is going to repeat this node, right? Now from the right also, if you start, the same thing happens. From the left or right, any vertex you start a cycle which contains all the vertices, it is going to repeat this particular vertex, so it is not going to be a Hamiltonian cycle there. Now this one, if you start with this cycle, this vertex, and form a cycle which contains all the vertices, it is going to repeat that vertex, this particular vertex, it will be repeated in that cycle 3 times. Therefore we don't have any Hamiltonian cycle here. This graph is not Hamiltonian. So it's neither Hamiltonian nor Eulerian. It's a connected graph which has cycles. So such graphs also exist.